Hello, happy people of the statistics world. Today we're going to talk about the empirical rule. This is our second video for our virtual days. If you hear some weird sounds, I believe they're replacing the floor above me. So I promise you my apartment's not falling down, nor is anyone getting murdered above me. They're just replacing the floor. So today's going to work the same as we've done before. We're just going to go through the slides that I would have and the examples I would have gone through in class. And then you'll have an assignment to do. And remember to take a picture, put it on a Google Doc, and share it with me. So on this slide, you're going to want to write down what the empirical rule is. I'm going to stop talking for a moment so you can pause the video and write down anything you need to. If the picture is too small for you, I do have another slide with the picture bigger for you and an explanation of how the picture works. So there you go. All right, the empirical rule states that when we have a normal distribution, usually for our mean, we're going to use mu. This one uses x bar, but that's okay. The empirical rule is the same either way. And we have our standard deviations. What's going to happen is a certain percentage is going to be for each standard deviation away from the mean. So first of all, the area under a normal curve is 1. And so that means basically we can find the proportion of the area, or we can think of it as a probability, where the probability under the curve is 100%. So all our data points are under the curve, and the percentage is a probability of our data point being there. So the empirical rule states that 68% of the area lies within one standard deviation of the mean, or 60%, 8% of the data lies within one standard deviation of the mean. That means if we add a standard deviation or subtract a standard deviation, that should represent about 68% of our data. Within two standard deviations of the mean, we should have 95% of our data, or we should have 95% of the area. And within three standard deviations, we should have 99.7% of our data, or 99.7% of the area lies within three standard deviations. This is also called the 68, 95, 99.7 rule. So if you're having trouble with the empirical rule and you're trying to look stuff up on your own, also look up the 68, 95, 99.7 rule. So like I said, on the next slide, I do have a bigger picture of that picture that was down below, and we're going to go through a short explanation of where all these numbers came from. So like I said, the empirical rule says that 68% of our data falls within one standard deviation. So remember, a normal curve we learned last time is symmetrical, which means it's the same on each side of the mean. So if 68% cover from minus a standard deviation to plus a standard deviation, each section for that must represent 34%. If we take our 95 and we subtract our 68 away, we're going to end up with the number 27. So there's 27% added on in each direction, that leaving 13.5%. So 27 divided by 2 is 13.5. If we take our 99.7 and we subtract our 95 away, we have 4.7% in each direction. So each section there is represented by 2.35%. And if 99.7% of the data falls in between three standard deviations of the mean, anything beyond that, there's only 0.3 left. So on each side must be 0.5%. We're going to use this graphic a lot because what it allows us to do is easily find the sections of area or probability that we're using, and we can add them up to find our probability. So that's what we are going to do today. So This first slide gives you the steps that we are going to use, and the next slide will use this example, and we will go through that. So I'm again going to pause so you can pause the video and write down 4 steps, and then we will go through the example using these 4 steps, and then I have a couple more examples for you so you know what you're doing when you have to do it on your own. All right, so for all of our problems today, we are going to sketch the normal curve. It's kind of hard for me to label the normal curve on here like I normally do. I will try, but if you look at the slides on Brightspace that I gave you, they will have it labeled, and that makes your problems easier if you label them. We're going to shade in what they give us, and then we're going to use that that graphic that we just had above to find the percent of shaded area, and then we're going to turn that percent into our probability by dividing by 100 or moving our decimal point twice. So like I said, we're going to do this example first. So we're going to find the probability that our data value is between two standard deviations below the mean and the mean. So first, like I said, we are going to draw a normal curve. It does not have to be perfect. It just has to be a bell-shaped curve where we can put our mean, and this would be +1, +2, and +3 standard deviations. This would be -1, -2 standard deviations, and -3 standard deviations. So we want to know what's the probability that you are bigger than -2 standard deviations, but between them and less than the mean. So that means we're going to look at these 2 sections here. And all we have to do to find our probability is we have to add up the sections that we had before. So if we look back at our graphic we had before, we would find out that between -1 standard deviation and the mean is 34% of our data. And between our -2 standard deviations and our -1, that represents 13.5% of our data. So if we add those 2 numbers together, we get 47.5%. And if we move our decimal place twice, that means our probability of our mean of our data point being between 2 standard deviations below the mean and our mean is 0.475. So all we're doing is we're adding up the sections that we know we have, and once we add them all up, we will have our probability. So I have 2 more examples for us to do together, and then I'll have you try it on your own. So the first one we're going to find is the probability that our data point is less than or equal to the mean. So again, the first thing we're going to do is draw that normal curve. So here's our mean, and we want to know basically what's the probability that we are down here. We could go through and we could sum up our 34% plus our 13.5% plus our 2.35% plus our 0.15% from our graphic, or we can just notice looking at our graph, since it's symmetrical and half of it is shaded, the probability that any data point we have is less than or equal to our mean is going to be 50%. That is what you get if you add up all those numbers. It's just doing a little extra work. So remember, we're trying to find the probability, or another way to look at it is 50% of our area is to the left of the mean. Right. I have one more example for you, and then we will All right, so our last example is we want to know the probability that any data point is bigger than one standard deviation above the mean. So if we draw our normal curve, remember our mean is in the middle. There's one standard deviation, two. Here's 1, 2, and 3. So this is 1, this is plus 2, this is plus 3. So we want to know what's the probability that we are bigger than one standard deviation above the mean. So really we have 3 sections shaded in there. We have the section in between one standard deviation and 2 standard deviations, which is 13.5%. We have between 2 and 3 standard deviations, which is 2.35%. And we have anything past 3 standard deviations above the mean, which is 0.515%. So if we add all of those numbers together, we get 16%. So our actual probability that any data point is above one standard deviation above the mean is 0.16. So whether you're trying to find a probability that's between two things, is bigger than one thing, or less than one thing, all you have to do is add up the sections and you should get your probability using the empirical rule. Tomorrow we're going to talk more about the empirical rule with actual numbers and using real life examples. So I hope you are all safe. I hope you're all healthy, and I hope you all have a great day. And don't forget to take a picture of the homework that goes with this and share it with me.